I am Anil Kumar. Welcome to my series on mechanics. This is a part of curriculum for GCSE Level A students. We'll discuss constant acceleration and its applications in this particular video. In case you want to learn from me, you can always send an email on the address given. We'll be uploading new videos on our website globalmathinstitute.com. In this lesson, we'll learn about how do we derive the formulas related to the constant application. So that will be the main thing. And once we derive the formulas, we'll take up some application questions. Now on this page, you see the summary of what we are going to learn. It's a good idea to begin from here itself, since it will review what we had learned earlier. As you know, velocity is rate of change of position. So it is displacement divided by time. So change in position is called displacement and change in time we'll write as delta t. Acceleration is rate of change of velocity. So this delta represents the change v2 minus v1, or in our document we have used v for final velocity and u for initial velocity. So the average velocity which we are talking about is initial velocity u plus final velocity v divided by 2. That gives you the average velocity for the duration in which the particle is moving. We'll assume linear relation for velocity with constant acceleration. The displacement for this will be the average velocity into time taken. We'll derive these formulas, which is v equals to u plus at, s equals to ut plus half at square, v square minus u square equals to 2as, and s equals to vt minus half at square. As I was saying, for constant acceleration, that means a horizontal line for acceleration on the acceleration time graph, will have a velocity which will be linear, as shown here, and the displacement will be quadratic in nature. So that is how they're related. You can also see from the equations derived that the velocity is linear equation, correct? And the displacement is a quadratic equation in time, correct? We're talking about the graph with time as independent variable. We'll take up many word problems. This includes a sketch of one of our questions. Now let's begin with the derivation of the formula. So we'll talk about the constant acceleration and velocity relation. Now when I say that the acceleration is rate of change of velocity, and I'm also saying constant acceleration, it means what? Well, when the acceleration is constant, the rate of change of velocity is constant, correct? Now that happens only if we have a straight line for velocity, right? So this implies that the velocity time graph will be a straight line. You get the idea, correct? Important to note. Only a straight line, which normally, the line equation is what? Y equals to mx plus b, correct? So here, m is the gradient. That represents constant acceleration. You get the idea. So whenever we are saying constant acceleration, the function is linear. It has to be a linear function for velocity. Perfect. Now, that helps us to derive the very first formula. If u is the initial velocity and v is the velocity after time t, then acceleration, a, is the gradient, correct? Which is delta v over delta t. That is final velocity minus initial velocity divided by the time taken. So let's say this time is t here from 0 to t, right? So this is delta t for us, and that is v minus u. You get the idea. So we get the gradient from the velocity as acceleration. So acceleration is v minus u over t minus 0. And this can be simplified. A equals to v minus u over t. Just cross multiply. So at equals to v minus u. And this gives us our first formula for velocity, acceleration, and time relationship. Is that clear to you? So velocity at any instance of time is equal to the initial velocity plus acceleration times time. As you can also see, it clearly indicates that for constant acceleration, velocity time graph will be linear. So this equation is a linear equation in time. Now, from this formula, we will now derive all other formulas, correct? You already know that what is the average velocity? Average is initial plus final divided by 2. So we have this average velocity formula, correct? If s is the displacement, which is change in position, if s is the displacement and t is the time taken to move from A to B, in that case, what is s? The displacement. Well, the displacement is average velocity into time. Now, since you know average velocity is v plus u over 2, we just multiply by time to get the formula. Correct? So we have another formula here, which is a distance speed time relationship, as you have been working on with, for such a long time. So this is the standard relationship which we have used, distance speed time, right? So displacement, velocity, and time. Correct. That relationship which we have used here. Okay. Now, how do we derive other formulas? We already have v equals to u plus at. Now, the idea is that we have two formulas to work with. One is the displacement, which is s equals to u plus v over 2 times t. Correct. So we have these two formulas to work with. We can eliminate one of the variables and get the third equation. So it is the process to eliminate variable. We already have these two equations, correct? So let's say this is our one equation and this is the other equation, correct? This we said equation 1, this is our equation number 2. So let me write this as equation number 2. Okay. Now, to eliminate really means if you want to eliminate v, for example, in that case, v is equals to u plus at. So in the formula, I'm substituting u plus at in s equals to u plus v over 2. Correct? So once you substitute this, you have eliminated v. And what do you get to simplify? You get s equals to ut plus half at squared. Correct? So that is another formula which you get. S equals to ut plus half at squared. Very popular. Now, let us see how do we eliminate time t. Well, to eliminate time t, I will rearrange this particular formula and find what t is. So t will be equals to v minus u over a. Just rearrange the formula, right? So we get this from the original formula, which is v equals to u plus at. So let's rearrange this. We'll take away u from v and then divide by a. Then we are going to substitute this value of t in s equals to u plus v over 2. So that value of t has now been replaced by v minus u over a. When you multiply, you get difference of square. U plus v times v minus u will give you v square minus u square, and then cross multiply with 2a and s, you get 2as. Perfect. So a few steps which I missed here. I would like you to complete those steps. So we get another formula here, which is v squared minus u squared equals to 2as, correct? So we'll call this as formula number 3, this is formula number 4, and the last formula here as formula number 5. Now in this particular case, we have eliminated u, correct? So this time we eliminated u. Arranging the equation, we get u equals to v minus at. The equation which we are rearranging is v equals to u plus at, the very first one which we derived, correct? So rearrange and substitute. So when you substitute for u as v minus at, you get 2v divided by 2, which is just v, so multiplied by t, you get vt, and then half at squared with a negative sign. Perfect. So you get this formula. So that is how we derive these formulas which relate velocity, acceleration, and time with displacement, where acceleration is constant, right? So remember, we are working with constant acceleration whenever we are going to use these applications, right? So in the next video, we'll also extend this to vertical movement where A equals to G, right? The gravity force, which is 9.8 meters per second square on Earth. So we'll take some examples in the next video where we have constant acceleration but a vertical movement. Okay. Now it is important to understand here that from the relations for constant acceleration, we have a velocity time graph which is linear and the position time graph which is quadratic. Now how do you relate that? Well, we say position time graph is quadratic, and there you go. This equation is quadratic in time. You see that s equals to ut plus half at squared as shown here. So that is the position time graph which is quadratic, correct? So it's very important to understand that when the acceleration is constant, the velocity is linear, and the position is quadratic in nature. Well, those of you who have done calculus will understand it even better because rate of change basically means a derivative. Now let us take examples to understand how to apply these formulas. So that's the key. Example 1 here is based on this constant acceleration velocity relation, equation number 1 which we just derived. A particle accelerates uniformly from 2 meters per second to 6 meters per second in 10 seconds. Find its acceleration. Correct? So that is the question for you. It is a good practice to always write what is given to us. So when a question like this is there with us, we'll say a particle accelerates uniformly. So we know A is constant, so we can apply these formulas. From initial velocity is 2 meters per second, the final velocity is 6 meters per second, right? In 10 seconds means delta t, the change in time is 10 seconds. Now, all this is related with our formula, which is acceleration, right? So acceleration is change in velocity over change in time, just as we derived it. So we can just substitute the values. Change in velocity is final minus initial velocity, correct? Substituting the values, we get the answer, which is 0.4 meters per second square. So I hope that is absolutely clear, right? Now let's take example 2, which is a bullet is fired straight up with the initial velocity of 400 meters per second. So in example 2, let's write down what is given to us. So the initial velocity u is 400 meters per second, correct? If it reaches the maximum height of 8 kilometers, so the displacement in this case is 8 kilometers. In 40 seconds, delta t is 40 seconds. Find the acceleration of the bullet. Well, in this case, which formula can you use? Well, there are a couple of formulas you can use, but there's one more important information. Maximum height, right? So I want to make use of this statement, maximum height of 8 kilometers. So when a bullet reaches the maximum height, let's say kind of like this, right? So it is going upwards and now it will fall from here. Is that clear to you? So at this particular point, the final velocity v has to be 0. You get the idea. So the final velocity is 0. That really means we could again use the same formula as we applied earlier, using the initial velocity, correct, the change in time, and final velocity. We may not use the displacement of 8 kilometers and use this particular formula to find the answer. You get the idea, right? So that is how we are going to do it. It is much, much simpler. So I hope you understand the concept. So again, the same thing as we did earlier. We'll just substitute the value of 0, in this case for the final velocity, initial being 400. But what you notice here is a negative answer. We get 10 with a negative sign, meters per second square, right? So the negative answer, which you see here, is indicating that the final velocity is less than the initial velocity. Correct? So this is referred to as deceleration. It's like braking, right? Your velocity decreases. So when you throw a stone or when a bullet is fired, it is fired with a very high velocity. But when it reaches the maximum height, it becomes zero. That means the velocity decreased, and that is deceleration, right? So it indicates that the final velocity is less than the initial velocity. Very important point to be noted, and that's why we have taken these two examples side by side. Now remember one more thing which is extremely important. In all our examples, we are considering everything as a particle, even this bullet, right? So we'll consider, let me write down here in bold, consider bullet as a particle. Now, when I say consider bullet as a particle, that really means what? That is what we need to understand, right? So here, particle is defined as an object with negligible dimensions, right? So you know bullet has weight, right? When you fire the bullet, then there's a lot of heat produced, there's friction, there is air resistance, everything is there. But while we are solving these questions, we will assume that it has no dimensions, kind of, right? Negligible dimensions. So the particle is defined as an object with negligible dimensions where the rotational forces and air resistance can be ignored. Correct? That is kind of very critical. So the rotational forces and the air resistance can be ignored, right? So it's like throwing it in the vacuum. Okay, you understand? So it's kind of like this. And the mass of the particle will be concentrated at a single point. That is an assumption. So these are our assumptions. So all the objects in this video, which we'll consider maybe a train, a plane, whatever, it will be considered as a point, right? With these characteristics. You understand? So all objects in our examples will be considered as particles. So even this bullet will be considered as a particle, correct? Where there is no air resistance when we are talking about application of these formulas. Is that clear to you? Correct? So that makes sense. Let's move forward to example number 3 now. If it says an object is moving along a straight line from point A to point B with constant acceleration of 0.6 meters per second. So we now A equals to 0.6 meters per second square. So as you read, write down what is given to you, right? That's the whole idea. The velocity at A is 4 meters per second. So velocity at A is 4 meters per second. Okay. And it takes 15 seconds to move from A to B. So change in time is 15 seconds. Find the velocity B and the distance from A to B. So we have to find the velocity at B and the distance S from A to B. Correct? These are the two things which we need to find. Now when you look at these parameters, think about the formulas. We have 5 formulas, correct? Which one to use where? Now, clearly, as you can see from here, we can use the change in velocity over change in time. Acceleration is given to us, and all these parameters indicate we can definitely use the formula where acceleration is equal to change in velocity over change in time. Perfect. So we are given the acceleration, we can substitute the values and then find the answer, right? So the velocity could now be calculated with using these formulas. Okay. Uh, so in our case, we have this formula v equals to u plus at. Now in this formula, we need to find the velocity. We know the initial velocity perfect, which is va, right? So we know u is equals to 4, which is va. So this is u for us. And we need to find the final velocity v, the formula which we are going to use is v equals to u plus at, right? So the final velocity v will be the initial velocity 4 plus acceleration 0.6 times the time, which is 15 seconds, and you directly get the answer, which is 13 meters per second. So you get the velocity. Now, to find the displacement, use the formula number 3, which was s equals to ut plus half at squared. You know the initial velocity of 4 times of 15, substituting these values, and we get our answer, which is 127.5 meters per second. Is that clear to you? So that is how these formulas can easily be applied. So we have seen the direct application of formulas. Now, let's look into some application questions. Here, in example 4, a car traveling at 30 meters per second passes a stationary police officer. The police officer starts to move at a constant acceleration of 3.6 meters per second square to chase the speeding car 2 seconds after the car passes. How fast is the police officer traveling when it overtakes the speeding car? So that's the question for you. Now, at times, sketching helps. So let us say the police officer is standing here, right? Let's say this is the point P where police officer is standing. The car is going past this point, let us say in this direction, correct? Now, what happens? We know that the velocity of this particular car, which is going, is equal to, let's say velocity of the car is 30 meters per second, correct? Now, it is in a time zone of less than 30 meters per second, and therefore we are saying it is speeding. So the police officer starts to move at a constant acceleration of 3.6. Now, as far as police officer is concerned, he moves at a constant acceleration of 3.6 meters per second square, and but he starts speeding 2 seconds after. So if the time taken for this is t, then the time taken here will be t plus 2, correct? So the police car starts the chase, but when they meet, they are at the same point. You get the idea, right? They are at the same point. So how fast is the police officer traveling when it overtakes? That means they covered the same distance, correct? So that is the whole idea. So let this distance be s. So the distance covered by the speeding car, we are assuming that to be a constant speed of 30 meters per second, right? So the speeding car will do the distance of 30 times t in time t, correct? Now to find the distance which the police officer is going to cover is ut plus half at square. Initial velocity u is equal to 0 for the police officer. The time taken t is t plus 2, right? Since the police officer starts 2 seconds later, so that is replaced by t plus 2. 3.6 is given to us as the acceleration, and so we have the distance traveled by the police officer. Now, both these distances are equal. So basically, what we are saying is that the distance traveled by the car is equal to distance traveled by the police officer. So we equate these two equations and solve. When you equate them, then there's only one unknown, t, to be found. We have a quadratic equation to solve. Simplify this particular equation, apply the quadratic formula. Of course, you get two answers. Well, the police officer starts after 2 seconds. So we know that the value of t should be, t plus 2 should be greater than 2, right? So t plus 2 should be greater than 2. So we have to take the value which is greater than 2. So in the calculation, you'll see that 14.4 seconds is the value which is appropriate for the time taken. Correct. Now, we need to actually find how fast is the police officer. How fast means the velocity, right? So velocity is acceleration into time. Since we know initial velocity was 0, right? So we know v equals to u plus at. Since u equals to 0, v is equals to at. And therefore, we are using this particular formula. We know the acceleration multiplied by the time calculated, we get the velocity as 51.8 meters per second. Perfect. So that becomes our answer. Is that clear to you? That is how the questions can be solved. Perfect. Have a good look at it and you can rewind and look into the description. Now let's take up the last example, which is a toy train moves past three stations A, B, and C, where A, B is 4 meters. So I'm saying distance between A and B is 4 meters, and BC is 12 meters. Distance between B and C is 12 meters. Time taken to cross the distance AB and BC is 2 seconds and 4 seconds respectively. This I have shown here as 2 seconds as the time from A to B and 4 seconds as the time from B to C. Find the velocity of the toy car at A if the acceleration is constant. So we need to find the velocity at A, which I'm treating as VA. This is an excellent question. I'd like you to pause the video, take it as a test practice question, correct? And then try to solve it. Now, in this particular case, we'll consider the sections from A to B first, right? So let's start with A to B, right? This section. Now, in this particular section, we need to find what VA is. We are given the distance between A to B and the time taken. So we can apply the formula S equals to UT plus half AT squared. Substituting the values, we get a relation between the velocity at A and the constant acceleration A. Correct? So that formula is A equals to 2 minus VA. That is how we have related this. So we got acceleration in terms of velocity at A. Ultimately, we have to find what the velocity is at A. Now, let us see the second section, which is between B to C. Now, in this section, the distance between B to C, the displacement, is 12 meters and time taken for this is 4 seconds. Now, we can say that the velocity at B is actually equals to velocity at A plus 4A. So that is the previous case, correct? So using V equals to U plus AT, we can write this relation, correct? We know V equals to U plus AT. So velocity at B is velocity at A plus 4A. Now that relates the velocity at B with the velocity at A. Perfect. Now, since we need to use the formula for the section BC as S equals to UT plus half AT squared, we have the term VB, the velocity at B, 4 times velocity at B plus half AT squared, right? Now, replacing this particular velocity at B with VA plus 4A, we have an equation again with velocity at A and acceleration. So we get the second equation with velocity of A and C. So we have these two equations to solve. Is that clear to you? So when you have two equations and two unknowns, it is not difficult at all. So in this particular case, we have used the method of substitution, right? So substitute the value of A in this equation. So we substitute the value of A, which is 2 minus VA, in equation number 2. So you have equation in the velocity at A. It comes out to be 1.8 meters per second. Perfect. So that is how it could be solved. So a question could have many stages to work with. So I hope with these examples, the concept is absolutely clear. You can always subscribe to my videos. Write to me on the email address given. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.